Okay, good morning, everyone. We are Team 57. Today, we are presenting the midterm problem statement, the vital extraction challenge. So, the problem statement was to extract the vitals from the image, like the heart rate, SpO2, systolic blood pressure, etc. So this is the pipeline of a solution. The pipeline of a solution was to first segment out the region of interest, that is the screen of the monitor, then pre-process the image. Further, we would classify the image using a CNN model. We would then pre-process the region of interest and extract the vitals using the PyTest library. So for the extraction of the health monitor, our first approach was to solely use the image processing techniques to segment out the screen of the health monitor, so as to filter out the necessary information displayed on the screen. But we soon realized that this was not working on the edge cases wherein image had a lookalike shape of the monitor and had some numbers. So we moved on to some deep learning. So so we moved on to some deep learning models like YOLO and Mask RCNN. Further, we chose Mask RCNN as it had better pixel accuracy. It was better at handling complex cases where the monitor was not aligned or the lighting was not proper in the image. And also, the Mask RCNN is also much more flexible than YOLO in the implementation case. Also, and on the left side, you can see the image. We had contoured the entire screen where the necessary information lies. So, further, my teammate San would explain. Would like to expand on this.
Thank you, Ninarjan. Now for the pre-processing of the image part, we segmented out the image and using the contours, we got the bounding window of the health monitor. Now for some cases, the health window so detected would appear slant or tilted, which we would orient and correct it using OpenCV. Further, we would generalize all the images to one dimension for further classification. Now for the classification of the image, we used a CNN model to classify the health monitor into four classes. We trained the model using classification dataset and then used the unlabeled dataset to check the prediction accuracy or the correctness of the model. The correct predictions were then added to the respective classes. Now my teammate Devansh is going to explain on this further.
Yeah. Now for the digit extraction part of the pipeline, we first pre-process the image. First, we crop to the part where one or more vitals were present and resize it to a certain aspect ratio. Then we converted it to a grayscale image. This helps reduce the amount of information PyTesseract needs to process, as the grayscale images only have one channel. Then we inverted the image such that the background is in white. We do it because PyTesseract is optimized to work with black text on white background. Then we used also thresholding, which converts grayscale images to binary image that helps in identifying the edges of the digits. Then in the next step, we use opening morphological operation, which is basically eroding the image and then dilating it further so as to remove the isolated pixels from the image. This helps in denoising it. Then finally, we use image to string function by PyTesseract library. This converts the image to a string of characters, and then you can simply run a loop over the extracted string to extract digits from it. So here you can see the result of the image in the left. It has detected HR, SBP, DVP, MAP, SPO2, and RR as required. Thank you. This is where we conclude our presentation. Now, if you have any questions, you can present.
So, on like, okay, like, so, like, great job, guys. So, this one, like, you said, like, can you go to the slide where you presented about like tilting and all? You said like you used OpenCV to like correct the tilt and all. Like, what did you do over there?
So here,
Yes, like, so you said like no, even before that, like you use OpenCV to correct the tilt and all.
okay, sir. Actually, we tried to use perspective transformation there.
Okay.
Okay, so the question is like for perspective transformation, right? You need to know the coordinates uh,
Yes, sir.
to correct the tilt. So how you are getting those coordinates? How you are predicting those?
So actually, we are approximately trying to get the coordinates. Like for the previous example here, here we actually manually like did this thing. Like here we the monitor is segmented here, right? So for the cases like the monitor which is lying here, we were trying to like rescale it and then use the coordinates there. So from the annotation itself, like we are getting these coordinates, right? So from the from the boundary box, we are getting the coordinates, and using this coordinates which we got from this image, we then use the perspective transformation to get here like this.
But like that won't be like generalized, right? Like so we had also given segmentation data set as well to, so you could have used some like model to like learn that.
Yeah, so we can learn it, but like probably if we use the bounding rectangle function of the OpenCV library to get the coordinates, it would be probably much better accurately like define the perspective transformed image, right? So that's why we use the bounding rectangle function to get the coordinates.
Also, the mask CNN model which we had trained it on segmentation dataset itself.
Okay.
Yeah.
Okay. Thank you guys. Thanks.
Okay, sir. Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
So we'll be getting the next team, right?
We actually like finished earlier, so might have like few minutes.
That's okay.
And we can have 5 minute break.
Hello, Nathan.
Yes, Jitesh.
So, Akansh, can we have the next team ready? So,
Like,
some teams would be finishing soon, some teams would take some. So, can we have like a next team like ready?
just a minute, Jitesh, I'll confirm.
Okay.
Sir, can you please confirm the team 47 is not in the waiting room?
Yes, the team 47 is not in the meeting room.
Okay, sir, just a minute.
Hello, Yashas.
Yes, sir. My other
Yes.
yes, sir. My other team members are joining. Right.
Okay.
Hello. Yes, sir. My other
Uh, Good morning, judges. So,
Uh, team 47, we request you to please listen to the bell. We will be ringing the bell at 8 and 9:30, at 9 minute 30 seconds. So please listen to the bell once.
okay, so I'll be start presenting.
Hello,
Uh,
good morning.
just listen to the bell, please.
Good morning, team 47. Yeah, you guys can start.
Is the screen visible?
Yes.
Uh, Excuse me, Jitesh. Rishi Jori is not following the nomenclature. So can you please remove him? He's not following the convention, like team naming
Okay.
convention. Yes. Please
Okay.
remove him. Okay.
Yeah. Okay.
So, hi, myself Alankat. So, today I'm presenting and starting the presentation for Cloudphysician. So, first of all, I'll give you the pipeline overview. So, what we did was took the images, the three data sets that were given. First one was for segmentation, second one was for the classification and object detection, and the third one was the unlabeled data set. So what we first did was we took the segmentation task and we did segmentation to capture the image screens, and then we applied classification to detect which of the screen it was, And then using object detection, we detected the regions where the uh, of a region of interest, like where the heart rate is written and where the graphs are. And further, we digitize the heart rate for brownie points also. So first of all, I'll tell you about how we generated a dataset for segmentation. So what we were given was 4 points, x1, x2, x2, y2, so on. So we converted them into Cocoa annotation, which uses it needs the area of the polygon. So we wrote a Python script to convert it into Cocoa annotation, and then we uploaded on it on RoboFlow and used augmentations with brightness variations up to -25% to +25%, blur up to 2.5 pixels, and noise of up to 1 pixels. So this would improve the model performance because there's a variation in the dataset. Then for object detection, we use PyTorch labeling since these were not any parallelograms or any other stuff. These were rectangles. So in PyTorch, it just requires the center and width and height. So here also we applied augmentation. Then again for dataset character recognition, we used our own cropped images. These images that are shown are from our model only. This is what we are getting after cropping. So first of all, segmentation. What we did in segmentation was we used segformer. Segformer is an library that is used for segmentation. So first of all, we trained them, and we got the results like in here it is shown approximately 0.98% accuracy. So this was trained by us, but then we what we thought was it would be better if we get it trained for longer hours. So we went to RoboFlow and trained it for about 12 hours to get 99.1% accuracy. So this is for segmentation where we are getting 99.1% accuracy. These graphs are from the RoboFlow model, and these were from the segmentation, the seg former. Then for object detection, what we used was YOLO V5. In YOLO V5, we had 4 label dataset for each screen, where these are the screen results, where the accuracy is about 91%, 97%, in 80%, depending on the screens. So about each dataset had approximately 4,200 images. Then these are the detected results. It crops the images, like it gets the OCR, like 80 is separated to 97 separated, 20 separated, and the graphs are also separated. So further, what we did was OCR, and like these crops were stored in a folder, and we did OCR and brownie points on them. So I'll hand it over to Yashasvi for OCR.
Thank you. So in the optical character recognition task, what we did was we used PyTesseract. One second. We used PyTesseract to overall detect the image, but there was some noise which we were getting, as you could have seen in the images earlier. So we had to do some noise removal and blurring kind of operations. So there, by after a lot of tweaking, we somehow managed to uh, detect the images, but then the images were still not that the results were still not that good. So we used some PyTesseract's inbuilt configurations. Now these configurations are pre-trained. There are different pre-trained models with different configurations which can be used for better results. Now I could see this 187. It doesn't look really like 187. The one really doesn't look like one. But after a lot of noise removal and blurring, this whole image was converted easily.
So continuing from Yashashva, I Anubhav will continue from the classification task. So first, let's what's classification? Classification task is a basic, fundamental classification task here, where we'll be classifying the different models into the 4 different models that has been provided to us. So we are using logistic regression here, which gives different probability scores to each of the class, and from there we pick the highest class, maximum probability class. So I have used the classic AlexNet model and modified it a bit by with adding a few hidden layers of max pooling and dense layers. So the activation function used is ReLU. Just only in the last activation function, I've used softmax to classify it into four different classes. So next, this is a classification model in which I have used regularization, L2 regularization to be specific, to remove overfitting of the training set so that it gives good results on the training set, validation test, as well as the test sets. So the optimizer used while compiling is Adam, and the loss function is sparse categorical cross entropy. What its difference from it's almost similar to categorical cross entropy. Only the difference is it gives in integers values. So that was the model summary. As you can see, it I have specified everything what have been used and the number of layers and parameters. So this was the training and validation dataset results. As you can see, it was giving excellent results from the starting. So and also it is giving excellent results in the tests for we have tested. So now let's go on the brownie points part, a heart rate digitization. In this first in the cropping section, we have cropped the monitor into different parts, and from here we are getting a graph. Only the graph image of the heart rate monitor. So what we have thought of doing is we have converted the raster image, which is pixelated, into a vectorized image. What I mean by vectorized image here is the classical vectorized images like SVG, where we use lines and polygons to form an image. So it's not pixelated. So even if you zoom it infinitely, it will never get pixelated, or it will never get the resolution will never go down. So what we have done in so I have made clear about raster images which are pixelated and what are vector images. So these are the steps involved that we have used in the brownie points. First, during the whole transaction, we have the ECG graph. We are scanning it, and we have been given the cropped image. That's the region of interest. So first we have binarized the image. Then like this is proper image processing where we are just thresholding the image, so we can convert this image into this image, which is the only information that we need for heart rate digitization. So next we have used a library from Python known as portrace, which I have used to trace the image. Here by tracing the image, I am meaning bitmapping the image, and bitmapping is a way of displaying the image and converting the pixelated image to vectorized image. So in in portraits we get two types of in portraits we get the image, and the image is divided into path, which shows the whole vectorized image. Then it is converted into the curves show a little closed figure in the vectorized image, and in curves are further divided into segments, which are bezier segment and corner segment. Bezier segment is like the image shown in the figure one. Like there's a curve, but there is not a sharp corner point. And in the second corner segment shows the sharp corner point. So from here we can find the ups and downs in the heart rate, and from there we can find the value of PQRS as we have to do in heart rate monitor. So this is the result from the graph that we have taken from the heart rate monitor. As you can see, it first gives me the start rate of the curve, and then it goes on to give me the different segments that are in the curve from the starting point and the ending point. And we are not giving the start end point of a curve because that is the start point of the another curve that is being shown below. Thank you.
So I would like to end with inference. So inference in what we did was we made functions and we compiled all the results, and this is what we were getting, like 88, 97, 64. This is all the extracted data that we got for the result. We end our presentation.
Okay, so for inference, right? So here it's showing like RR wave rate. Actually, it's a heart rate wave rate. So
Yeah,
how you're like classifying these like waves?
like for classification, like first of all we detected the screen, and then we were given the object detection data set, right? Of like there was marred regions. So it was trained, and then this is what it was giving. Like it is a very good accuracy. About like other things, it is getting quite accurately. And there's a small, a slight error also in the data set. Like in the RR, we're missing a small thing. So like there were 9 classes. We took 8 while taking this image. So it's just a small error, I guess. It will get okay, I guess.
Okay, so also you have like mentioned you have used PyTest. Like, so how you are like denoising those images for PyTest? Like, because I think PyTest like require very high contrast to like predict.
So
So
what
what
we
we
are
are
doing
doing
is
is
we are giving a color 2D map. So what it does is using convolution, it enhances the image boundaries. So when we get the image boundaries, then we are doing is we are thresholding the image into a binary image. So now we have enhanced boundaries using that color map. So now OCR is much better than applying it on the raw image. So that is how we are removing the like noise around the boundaries.
So sometimes what's happen is like those images are not that sharp and clear, right? So yeah, it's even from like raw data, it's like blurred image. So how denoising is going to like happen over there? Because it will be like blurred digit, so you won't be able to like find sharp edges over there.
So
Yeah,
in that case, what we are doing is like we are using the edge detectors. So edge detector, even if we get a slight edge detecting, like we do in canny edge detector, we smoothen the image, and we even if we get some part of the image, we can recognize that and convert that into the text using the OCR code that we have used.
Okay, okay. Okay. Jitesh, do you want to?
So on the classification task, right? Like, can you like tell me like why you guys have like used AlexNet like amongst other things? Any a particular reason why you chose that?
So there are many classification models like LeNet, AlexNet, and many other. And AlexNet is not a very popular and recent classification model, but I have not used AlexNet as my classification model. I have used as a base model and built on it. Like AlexNet gives very fine results for classification, but nowadays for improving speed and adding hidden layers, it's very nice practice to use AlexNet and build on that project. So, and I am very accustomed to using AlexNet. I have used AlexNet in my previous projects also. So, building on AlexNet was a good practice for me. So, I went up with AlexNet, and fortunately, I got great results while doing so.
Okay.
And sir, one more thing. For about like we talked to the event like manager. So he said that we didn't get the chance to talk and rectify our code. So can we just show you our code demonstration, because the code that was submitted we were getting a small error.
Um. So I would like say like no, because like this is supposed to be just be presentation, right? So
Yeah, but he said
uh,
like because we didn't get the chance earlier to interact, so we can do it now.
who said that?
I guess Abhinav.
Okay.
uh,
Um.
I am here.
Yeah, so I'm Alankrit. I like talked to you like yesterday.
I mentioned specifically that if you want anything with code, you can do it in the presentation time. For the Q&A time, it will be entirely with the judges.
Yeah. So so on
Then I
that,
guess
right?
like we will just get 10 seconds, if you want to say like, get it just consider it as a part of a presentation. Then I was not you didn't like clearly mentioned it earlier,
I think we
because
had
the
a telephonic discussion over this. Let's not go over it again. I think Jitesh sir, please continue with your Q&A.
okay.
Okay. So like we are done with the Q&A. So we can go on to the next one. Thank you guys like for working on this a great presentation as well. Thanks a lot.
Thank you, sir.
Thank you, sir.
Thank you, sir.
I request Team 49 to please listen to the bell. We'll be ringing the bell at 8 minutes and 9 minutes 30 seconds. Just a minute. Okay.
Okay. Okay. Good morning, team. So this is team 49, right? Just 1 minute. Um, yeah. Good morning, team. So you can start.
Good morning to one another present over here. So we are Team 49 and the main topic of our mid-term problem statement is Cloudphysician, the vital extraction challenge. So the main objective of our mid-prep statement is to extract the data of the vitals of the human beings like heart rate, SpO2, RR, SBP, and all the other 9 major features from the monitor screens of the patient monitoring systems. The background around this is that this is the part of the cloud physician pursuit of creating smart ICU solutions. The entire problem statement has been created on a proper pipeline that is divided into 3 major stages. The first stage is monitor screen extraction, the second stage is feature extraction, and the third stage is text recognition. And adding on this, we have the graph digitization part of the heart rate, and this is to extract the information from the waveform of the waveform based vitals. Talking about the data set, we were given 3 types of data sets. First being the monitor data set, second being the classification, and the third being the unlabeled data set. The monitor data set consisted of 2000 images, and we were given the coordinates for the same. The second being the classification data set, we had 4 folders, each consisting of 250 images and the 4 data files, which consisted of the features of the 9 vitals of the human beings. And the unlabeled data set consisted of 7,000 images, which we weren't given the coordinates for the same. So let's have a look at the null values that we received from the all the 4 sets: set A, set B, set C, and set D. And on the first image, you could see where we are segmenting the monitor screens from the same.
Yeah, so moving towards the main part of our problem statement. So this flowchart depicts the main pipeline which we have built to solve this problem statement. So in this pipeline, the first stage is the input images that the user gives us. And the first primary stage of our pipeline is the monitor image extraction model represented in this blue box. So this is the model 1 of our pipeline, and this is basically a YOLO V7 model which was trained on the initial 2000 images given. So the main feature function of this model is to predict the bounding boxes of the monitor screen from the input images, and we use those bounding boxes to extract the monitor screen from the input images. And then these extracted, the cropped monitor screen is sent to the second stage of the pipeline, which is the feature extraction model represented in the red box. So this feature extraction model intakes the predicted output monitor screen from the first model, and then it predicts various different vitals in that particular monitor screen. So basically it predicts the bounding boxes of all the individual features in that particular monitor screens and store these individual feature bounding box coordinates into a particular data frame. And then this data frame is sent to the third stage of our pipeline, which is the feature retrieval part. Basically this feature retrieval part intakes 2 inputs. First is the data frame, which consists the bounding box coordinates of each of the predicted features in the monitor screen, and second is the monitor screen itself, which was the prediction of the monitor image extraction model. So this feature retrieval part, we actually use those predicted bounding box coordinates to extract the individual small images of the predicted features, and then we apply easy OCR techniques to actually get those numbers out and store them into a dictionary, which was our desired output. And also this includes the graph digitization part, in which we extract the first the graph from the image using the predicted bounding box, and then we apply some clustering techniques to digitize the graph, and that was the final result that we get. So moving further towards the model 1, which was the first stage. So this is the monitor screen extraction model, which I've already told is a unique classification YOLO V7 model, which is object detection model, and it was trained on 1800 images with a validation set of 200 images and around 35 epochs, because it has just only one class to predict. And the it outputs a tensor which contains the bounding box and confidence score of the predicted monitor screen. And moving towards the second part, which is the model 2, the feature extraction model. So basically, it is a multi-class object detection YOLO V7 model, which was trained on the 1,000 images. So in which the training set was 800 images and validation was 200 images. And this has a particularly large number of classes. So we use 45 epochs to train it, and it outputs us a tensor, which gives us the predicted classes bounding boxes along with their confidence scores, and while filtering out, we take the highest confidence score classes for creating the data frame, and then we pass it to the feature extraction part. And moving towards the results, so the overall results depicts like the inference time of the whole pipeline of running the model, excluding the loading of model, is around 3.5 seconds, and the model wise results is shown here, the F1 score of both the two models. And these plots basically depicts the individual performance of both the model, which actually depicts the whole performance of the pipeline, and which we can see is pretty much accurate, the confusion matrix and all.
Okay, so further moving on to text recognition, how exactly did we extract the text? So we use the easy OCR model, which is basically based on the optical character recognition colored images as the input. So for cases as mentioned in the slide, there is a character like a bracket apart from the numerical values for the value of the vitals. So to remove that character, we basically try to convert the string to an integer, and whichever character prevents the integer conversion, we remove it from the string, which renders us basically with the integer or the numerical value. And the main function in the easy OCR that allows us for the text extraction is the reader.read text function. So we ultimately achieve an accuracy of 75 to 90% for the text recognition part.
Yeah, so talking about the graph digitization part, the process of digitizing the heart rate graph in the image involves several key steps. Firstly, the relevant portion of the image that contains the heart rate graph is cropped using the provided bounding box coordinates from modern 2. Subsequently, a thresholding technique is then applied to differentiate the graph lines from the background by determining the color of the graph lines through the use of k-means clustering algorithm. Then the binary image is further processed using morphological close operation to define the graph lines and remove swan gaps. The coordinates of the graph lines are then extracted, stored in a data frame, and duplicates were removed. Then we applied DB-scan algorithm to cluster the graph point based on the spatial proximity, and kernels were assigned to distinguish each cluster. The visualization makes it easier to identify and interpret the data patterns and group them into meaningful clusters, helping us to eliminate any unwanted noise present in the graph. So as you can see, like this is the bounding box for the heart rate graph, and after applying the graph digitization function, we get graph like this. And here we have two colors, one is blue and one is orange. So it separates noise in form of colors so that we can easily see what kind of noises are there in the original image. Thank you for giving us this opportunity, and here we end our presentation.
Thank you, guys. So on the easy OCR, right? Like one was about like the symbols. So when you're like trying to do like BP, there's this 123 forward slash 77. So did you were you able to like so sometimes like that if you when you're converting it into like integers, when you ran into like those cases, did you see anything? Were you able to tackle those cases? So sometimes that slash might be like be interpreted as one, or like sometimes it will not be. So how did you like tackle those cases?
Yeah, so for those particular cases, like we saw in SBP, basically for those corner kind of cases, we could see that there were up to three characters. It was a numerical value, and the fourth character was detected as a slash. So by that method, we tried to limit the number to the first three characters only by accessing only the first three characters to give us the required output, so that we could get rid of the
Sometimes
slash.
sometimes like SBP, if you're going to consider like three characters, it can also be that the SBP has only like two characters, 99 as well. So then
Yeah, so I think we sort of did a bit of an analysis, and there we kind of found that it is mostly up to 3 characters for the like data set that was provided, and hence we considered that to be a general case and took it up to the first 3 characters.
Okay, okay.
Okay, so for segmentation, right? So you have used YOLO 7 model. So it is you are saying it is giving high accuracy. Okay, but like sometimes what happens is like monitor is tilted. So it YOLO 7 will only give you like bounding boxes. So how do you like tackle those cases when monitor is tilted? Because like when you do OCR and even like this graph extraction, right? It will overlap over the other digits or other graphs.
So actually, when the model is tilted, it actually predicts the bounding boxes. But in most of the dataset images that we looked, the tilt is not too much that the features actually overlaps on each other. So it gives us a like accurate monitor screen, and then we can individually extract the individual features. And if overlapping of different feature happens, which generally doesn't happen, then generally we take the highest confidence classes of each of the individual features. Like due to make some accuracy, like SPO2 or other may be detected twice or thrice. So in a particular image, so then we take highest confidence scores to get the like more accurate value of every particular class. And the tilt thing is like it's not specifically deal with YOLO V7, but mostly in generalizing, we saw that most of the monitor screens were not that too much tilt, and for little bit tilt, the YOLO V7 model was actually working pretty much fine.
Okay, so do you have like any analysis report for that one? So you are saying like it's most cases, right? So that word is not actually like giving more of the information.
We just observe the data set by running it on multiple unlabeled images as well, like looking up some like different images in which screen were not visible. Like we don't have a documentation of that because that's a like corner case. So what actually it worked pretty well on some unlabeled images as well, in which the monitor screen was not actually visible. So I think that's all we.
So one more question was that so for HR digitization part, you are using DB scans. So that will give you like points, right? But the graph is like continuous. So how do you like form a continuous graph from points?
Yeah, so it will give us point in form of clusters. So we will use dot not function of matplotlib to plot the points and from a straight line graph, as you can see in the graph digitization.
Okay. Thank you, guys.
Okay, thank you guys. So we can close this. Thank you. Thanks a lot.
Thank you, sir.
Thank
Thank
you
you so
so
much,
much.
sir.
Thank you.
Thank you.
Good morning, Team 45.
Good morning.
Good
Yeah.
morning.
Hello. Are we audible? Yes.
Yes, yes. I think like the organizers
Yeah, we
might
are
have
audible,
like
right?
something.
Team 45, I request you to please listen to the bell. We'll be ringing the bell at 8 minutes and 9 minutes 30 seconds. So the buzzer is, it goes like this.
Okay. All right.
Okay.
So can we start?
Okay, yeah. Yeah, please start.
Yeah. Good morning, everyone. We are Team 45, and this is our solution for Cloudphysician's The Vital Extraction Challenge. Our solution aims at accurately extracting vitals with minimum inference time while being robust to multiple screen layouts. We have divided this task into four stages: the screen extraction, the digit localization, the digit recognition, and the vital mapping. Our solution consists of two modes: the fast mode and the accurate mode, which has a trade off between accuracy and inference time. The pipeline for the accurate mode is shown here. As we can see here, we take the input image and pass it through a corner regression and unit plus plus model, whose outputs are then assembled using area union fusion to get the screens. The extracted screen is then passed to YOLO V5 model and a paddle OCR using weighted box fusion to get the bounding boxes around the digits on the screen. These bounding boxes are then passed to Parsec OCR for reading the numbers in the screen in the bounding boxes. This information is then passed to our custom novel CrabNet model for mapping numbers to the vitals. Moving on to the first stage, the screen extraction stage. This is the stage where we extract monitor screen from given images. We have used ensembling of two modes methods, unit plus plus and corner regression, using area union fusion to get the screens. Corner regression uses a ResNet34 backbone to take screen as input image and regresses over the coordinates of the bounding box to give output of length 8. We have implemented our modified versions of custom horizontal flip and random crop augmentations to perform better on edge cases where model generally fails. Next, we have used semantic segmentation using unit plus plus with a custom combo loss combining dice loss and BCE loss for increasing IOU and confidence score of the predicted mask. Several pre-processing techniques are then applied, like flood fill and morphology, to fill the mask, smoothen it, which is then used for predicting the bounding box using contour detection. The prediction of both corner regression and unit plus plus are combined using area union fusion, which generates the smallest bounding box enclosing both the predictions to prevent loss of information. The inference time of the screen extraction stage is 5.24 seconds with a mean IOU of 0.91. This is an example of how area union fusion helps in preventing loss of any part of information. As we can see, unit plus plus is not performing well on this part of the screen, while regression does not perform well on this part of the screen. Hence, the ensembling performs well on all the parts and gives and prevents any loss of information. Next comes digit localization. So after screen extraction, we have to localize the vitals present on our screen, for which we have used the ensembling of outputs from YOLO and Paddle OCR. An important thing to note here is that we have used YOLO for only extracting the numbers and not for classifying them. Out of the different options available, we chose YOLO V5M due to its lesser inference time, around 700 milliseconds, and a better precision score. We fine-tuned YOLO on the given 1000 images and other 500 annotated images that we selected using a low confidence threshold. So to improve the detections from YOLO, we ensemble the results with pre-trained Paddle OCR's detection phase. Paddle OCR uses DBNet as its backbone for detection and has an inference time of 300 milliseconds. As we can see here, it also detects some boxes containing noise. So we have used an algorithm called weighted box fusion to combine the outputs from both of our object detection models. This algorithm takes the confidence scores of all the bounding boxes as weights and constructs weighted bounding box around the numbers. This ensures that no vital numbers are being missed. And finally, we use a filtering algorithm designed to remove boxes containing noise using output obtained from our digit recognition phase. After this step, we are only left with boxes containing vitals. The inference time of this stage of our pipeline is 1.6 seconds. And here is an example of how we have used weighted box fusion and filtering to improve the results from YOLO and Paddle OCR. Next comes the digit recognition phase. So after creating bounding boxes around the required values, we read them using Parsec, a scene text recognition model.
It proved to be better than other models while reading information from obscure images which had misaligned text, just like these examples shown here. We also used batch inference to improve the inference time of this part of our pipeline by 23% to 880 milliseconds with an accuracy of 98.4%.
Okay, so now that we have found all the numbers on the screen, detected and read them, we need to classify each recognized number to a vital. Here, each vital is one class. For this task, we need a model that takes the image, all the bounding boxes, the numbers to be classified, and all other recognized numbers on the screen as input. To use all of this information simultaneously, we created our custom architecture called CrabNet. So let's look at how this architecture works. First, we create a binary mask of the bounding box of our target number. The target number is the number we want to classify. So this binary mask is then stacked as the force channel with the image, and this force channel input is passed to a Resonix 50 backbone to give an output of 2048 size. This feature vector is concatenated with another vector of size 14. This vector consists of the number to be classified, associated symbols like brackets and slash, which are generally found with BP readings, and all other numbers on the screen. This 14 size vector is passed through a linear layer to get an output of size 6. This size 6 output, along with the number to be classified, is again concatenated with the 2048 size feature vector to get a vector of size 2055, which is finally passed through a fully connected layer to get our 6 classes. An interesting thing to note is that the number to be classified is passed twice in this model so that the model learns to give more weightage to it. And the bounding box helps the model to learn the local features of that number. For each recognized number, the CrabNet returns the corresponding scores corresponding to the classes. If we try to classify each recognized number to a class separately, then there is a possibility that two recognized numbers get the same class. So we need to take this as a mapping task and not a classification task. To do this, we developed a custom logic decoding technique for multi-label mapping. In this technique, what we do is that once we have the confidences of all recognized numbers on the screen, we find the most confident class by checking the class with the highest variance in confidences of all numbers for that class. Then we assign that class with the number with the highest confidence for that class. Then the assigned number is deleted from the output, and this process is repeated till we have assigned all the recognized numbers on the screen. The inference time of CrabNet and our custom logic decoding technique combined is around 1 second. The 4 stages that we have covered so far explain the accurate mode of our pipeline, and now we'll move to the fast mode of our pipeline.
As discussed earlier, the fast mode of our solution makes sure that the output is generated within 2 seconds of CPU time. By default, the solution is set to work in accurate mode, which can be changed to fast mode easily. In fast mode, we first take the input image and pass it to the corner regression model to extract the screen. The extracted screen is then passed to a YOLO V5 model, which is trained to detect numbers on screen along with assigning them to the respective vitals. These bounding boxes of detected vitals are then passed to a paddle OCR for recognizing the values inside them, which is then given as the output. Here is the example of the output of YOLO which we trained for our fast mode. This YOLO model improves the inference time to a great extent, but was not able to perform well on unseen layouts, that is, new layouts on which model wasn't trained on. Here is the comparison of both our models of our pipeline. As we can see, the accurate mode provides an accuracy of 89.7% with an inference time of 8 seconds, while the fast mode provides an accuracy of 74.1% with an inference time of 1.57 seconds. We have also experimented with the graph and found that it works well in some layouts. Here is our approach. We have used fine-tuned YOLO V5 model to detect graph from the screen. The detected part of the image is then cropped and passed through filters like grayscaling and binary conversion. This pre-processed image is then used to find the contour of maximum length, which is then interpolated using cubic spline algorithm. These data points of the contour correspond to the data points of the graph on an arbitrary scale. Novelties. Besides our novel architecture of CrabNet and our novel logic decoding and mapping algorithm, we have used many fusion techniques such as weighted box fusion and area union fusion to ensemble output of two models for more accurate and robust performance. Our implementation of custom augmentations of random crop and horizontal flip also helped our predictions on the screen to give better performance significantly. These custom augmentations help our screen extraction model to perform well in cases where the monitor was too close to the edge of the image. Future works. Some of our ideas which we could not implement due to time constraint are as follows. We propose a 3 to 7 channel unit which will take image and provide segmentation masks for each class as the output. That was from our side. Thank you so much.
Okay. So, um, good job on like some of the novelties and all. So, so you guys have like proposed like two modes, like fast mode and like this one, and the accurate mode. So we can consider one, but like the thing is, the notebook didn't like run. So that's a problem. So uh, like so yeah, like which one do we have to like consider? Made code changes and like load more. So yeah, but apart from that, like I just had like can you like explain more
I'm sorry,
about
could
that?
you come again? The notebook didn't run for like by default or for fast mode?
No, like the notebook hasn't run, right? So we were asking about that.
So we haven't like run on fast mode, so we wanted for accuracy, so we turned the default mode.
Yeah, so we had a meet with the yesterday because our notebook had a library installation error,
Hmm.
and in that our notebook ran for like around 15 minutes, and after that we disconnected because of time constraints.
Yeah,
I'm
so
not sure
actually,
what happened
yeah,
after that.
yeah. So actually, after like 20 minutes, it's giving a error in inference.
Yeah, but I think the results till then must have been recorded.
We will not. Yeah, that is there. Half of the results are there, but we can't like consider because it's crashing, right? At least it should give like zero or empty dictionary. But if you are giving throwing exceptions, so it's not the correct code.
Actually, we asked Abhinav also, like after leaving the mid, that is the notebook working fine, and he said, yeah, that the judges were satisfied with your notebook.
Not sure about that one.
Okay. Oh, just a minute. So this area union fusion ensembling, right? Like that's a custom one. Can you guys like tell us like how you uh, work this out?
Yeah, so basically in this, before till this stage, what we have is we have the bounding box from the corner regression task and the bounding prompts from the unit plus plus task. Okay, so we have the four coordinates, that is x1 y1 x2 y2. Similarly, we have four coordinates of both the methods. So then what we did was we combined so we found the minimum. So from for x1, suppose we found the minimum value of x1 of both of them, we considered that. Similarly, for y1, we found the minimum value of y1, and similarly for all the coordinates, we made a box which was best fitting both of the curves without adding extra information.
Okay. The post processing for this, like the uh, processing, like the segmentation and all of that. So that's like you guys have like used OpenCV for that, is
Yeah.
it?
Yes.
Okay. Okay. And so what you guys have used is like one image, right? Like how much like time does this like take? This piece, like the processing using OpenCV takes for an image?
This whole processing functions take around zero point 0.5 seconds to run.
Okay. Okay. Cool. Pradeep, do you have any?
Yes. So you have like a CREBNet architecture, right? So that was like custom architecture you have made. So here we are seeing like one assumption here. So it's data driven, right? Based on like data what is been like provided. The classification is based on like provided. So I think it's a little bit biased because like see numbers are going to like interchange their positions. So some images will have like interchange of the this position, but like most of images will give like same I mean the same position. So for those images where the number is being interchanged, it will misclassify those. So is there any
You mean interchanged by position on the screen?
yes.
Yeah, so when we are giving the bounding box as a mask, we are hoping that the model is learning color features also. It's learning relative position of other images also, of other numbers on the
Yes.
screen. And
Yes.
we are also giving the symbols and number itself, right? So like
Hmm.
for example, mean arterial pressure is generally written in brackets. So that is something our model learns really well.
Yeah.
So we are
So
giving as much information as possible so that we don't have such issues.
Uh, so not such issue means like it's not like a good term, but like see if you are giving the making this model as a data driven, so do you have any analysis on that data? So by using those features, do you have like a confidence score for like using those features as like a correct feature?
Uh, Analysis for interchanges.
Yeah, I mean like statistical significance, p-value. Did you have like calculated confidence score for that one?
We have not done error analysis for this, but what we know is that this model generally
Not
does tend to
error analysis. I am talking about data analysis. The
not
features
directly
that you
for.
have picked, right? So the mask you have picked and you are giving as a
Hmm.
color as a like a hyperparameter, right? That symbol you are telling about, like you can use those symbols.
Hmm.
So is there any analysis done?
Analysis like what I have done is that we have checked how each component, how this model functions without the components. For example, if I give only the mask and only the mask and image, then our model is
Okay,
actually
okay, okay,
20% less accurate. So what we know is that the more information we give, the better it performs.
okay, okay. That's good. Thank you, guys. Thank you.
Okay, thank you. We can close this. Thank you.
Okay,
Thank you
thank
all.
you.
Thank you so much.
Thank you.
Why is my screen visible?
Hi, hello team nine.
Hello? Hello. Good morning, team 19,
Yeah,
right?
this is team 19.
Good morning.
Good
Um,
morning.
yeah, okay. I guess like organizers would have something for you about like, yeah.
Uh, Team 19, we have the buzzer. It will be rang at 8 minutes and 9 minutes 30 seconds. So please listen to the bell.
Okay, got it.
Sure. Then like, yeah, you can start.
So we have to start at the buzzer.
No, you can start.
Okay, so good morning, everyone. I'm Ayush, the team captain of Team 19. And from my team, we have here Kushagra, the vice captain of the team, Ajinkya, and Mithun. Together, we present a solution to the vitals extraction challenge by the company Cloudphysician. Introduction to the problem. For healthcare monitoring, we need to keep a close track of all the vital signs of a patient, which is done by patient monitors. Thus, tracking the outputs of patient monitors is an important problem. So our problem statement is to extract different medical values from patient monitor images, namely HR, SpO2, BP, and MAP. So our team identified a wide variety of monitors, which included a lot of combinations of locations of numbers and a lot of color combinations. Some more particulars that we observed. HR is mostly in the color green and present on top of the images. SpO2 and RR didn't show any color consistency, but were close to the keywords associated with them, and RR was in the range 1 to 45. PP was always displayed with a slash in between SBP and DPP, and map was always found in brackets. These also followed the keyword trend. So we want to discuss some of the ML pipelines that we implemented and rejected. In the first one, we based the solution totally on the basis of colors of the numbers, like green with HR, etc. Unfortunately, we found a lot of exceptions, and images with alerts were also difficult to deal with. In our second pipeline, we approached the problem by classifying the monitors into four categories and using the location information to determine vitals. Unfortunately, the number of broad classes made this really inaccurate. In our third pipeline, which is very similar to our current approach, we use the words present in the image like the word BP, HR, etc., and observe the closeness to those words along with the location information. This is the visual representation of our first pipeline. As you can see, we are segmenting the image, then processing different resolution of images differently so that we can employ shallower models for high resolution images. Color recognition, OCR, and algorithmic logic is then run to get the vital output. This is a visual representation of our second simpler pipeline, and this is of our third pipeline. After segmentation, the binary classification was to be done for location-based and keyword-based detection differentiations. We tried different pre-trained models and trained different architectures. For example, a custom VGG16 architecture with dropout L1 and L2 regularization layers. It came really close to work, but they all suffered with the same problem of overfitting. All the working based on keyword is explained in our further slides, which is employed in our current pipeline. So for the final solution, we approach the problem as two subproblems, the first being the segmentation of images and the second being the detection of vitals on the monitors. Segmentation. For segmentation, we used CNN backbone networks along with the trainable CNN and dense layers on top of it. Some backbones that we tested and their RMS results. Some more techniques that we used to improve the performance of a segmentation. We padded all the images by 600 times 300 times pixels to eliminate errors in the cut images. We also applied an offset of 10 pixels to the predicted width in order to eliminate small inaccuracies. We also did skew correction by OpenCV to get better results for the OCR model. This is the graphical representation of our final pipeline. I would hand over the presentation to Kushagra.
Now I will start with the detection part. We had broadly two possible approaches to the detection part. First one, to train our own model to detect the text from the display. Secondly, use a pre-trained model or an OCR to detect the text in the LCD display. Since we did not have a large dataset, hence we decided to use an OCR. To get better results from the OCR, we started by pre-processing the images by various methods like edge sharpening, thinning the text, noise deletion, etc. But we didn't get satisfactory results. So lastly, we simply denoised the image and used it further. Now the biggest question came that which OCR should be used for a particular problem. Since we started experimenting with various OCRs like PyTesseract, Easy OCR, Keras OCR, MMOCR, but again, there were some issues with each method. Most of the OCRs weren't detecting the complete text required by us. For example, the easy OCR often failed to detect the slash, which was necessary for BP. And even the smaller keywords like SPO2 and HR, etc., was not being detected by it. So finally, we decided to use the paddle OCR. Now, the paddle OCR is based on a three-layer architecture, one being the style text, text detection, and the text recognition. The different models used for the above are present in the image, as shown. The architecture is based on a tesseract engine followed by a CRNN to recognize text by extracting features, then feature mapping, followed by sequencing the values according to their confidence values. Here, we get an output of a list of lists consisting of the coordinates of the bounding box, then the value or text in the bounding box, and then by its confidence value. Now, our main goal was to find out keywords in the image like HR, RESP, sys, map, dia, SPO2, etc. so that we can find out the bounding boxes nearest to these keywords. To detect the HR, RR, and SPO2, we are looking for the respective keywords first, and then using geometric functions such as segment to segment distance and box to box distance, we are finding the minimum boxes closest to these keywords. Now, if we couldn't find the heart rate using the above distance uh, method, then we take the possible heart rate boxes, find the most dominant colors, and if it lies in the range of green value, we declare it as HR. If still we couldn't find the HR, we take the value present in the top 30% of the image, and then we declare it as HR. For RR, if we couldn't find the value by keyword, we look for the value lying in the range 1 to 45. Our first approach to find BP is by looking for the keyword slash. If it is not found, we look for again the keywords sys and dia. For map, we are looking for round brackets. If not found, we are looking for the keyword map. Lastly, if still we are not able to find BP and map, we look for three numeric boxes whose minimum distance is less than a threshold. Now, this threshold was calculated by using a lot of various values and we experimented on a lot of different images. Now for the brownie points, we come to the ECG graph detection. For this, we first isolate the green color from the image and then draw contour around it and find the contour having the largest perimeter. And then we simply plot it. If not found, we simulate the graph using the heart rate value through the NeuroKit2 library. Now I would like Ayush to explain further.
Possible improvements that we could have implemented to further improve our results. Some more colors could have been used for better detection of vitals instead of using only green for HR. A classification-based approach could also have worked since location information could have been used in our models. And finally, if the binary classification model would have been developed properly, we could have achieved better results by employing a third pipeline. Now we have a visual representation of our working of a pipeline. So this is the visual representation of our working of our pipeline. It basically detects all the boxes near to the keywords and detects all the values according to it. So this
First of
was the
all,
end of our presentation. Thank you.
thank you. First of all, like good analysis. Um, so for example, like few things that you guys like pointed out, like that HR colors, like you guys like did see that, and the ranges as well. we like that like you also like uh, looked into like what would be like the ranges of like the values and particular attention to the BP, the symbols as well, like the forward slash and how to like detect that. So yeah.
Thank you, sir.
Pradeep, you can ask. I'll ask after you.
Okay, so I see like you're detecting BP, but you are also classifying like from multiple cases, right? So say for example, there is number like in blood pressure, and there is written text systolic and diastolic. So sys and dia is what is there. So how are you like associated systolic to like sys and diastolic to like I mean dia or
Uh, Mithun would answer this question. There seems to be some technical problems from his side. Yes, his mic is not working, I think. Just a second.
Yeah, sir. Can you repeat the question? Like, here your network was little bad. Like, can you repeat the question?
So for blood pressure, like there is a particular case where cis and dia words are there. So I'm asking like how are you like associate cis word to like systolic blood pressure number and dia word to diastolic blood pressure number?
Sir, like, sorry, I can't hear you clearly. Like, your voice is breaking for me. I don't know why. Like,
Oh,
I guess.
you able to hear
Yes,
me?
sir.
So Pradeep's question
Yes,
was
sir.
like,
Yes.
how are you able to like map systolic numbers to systolic and dialastic numbers to the dialastic one?
This word with cis dia in there. No? How are you associating cis word with systolic and dia with diastolic? Sir, yeah, yes, sir. Like how it is done is that like first we find the keyword cis or dia, and what we do is like we find three numbers. We have a threshold, so we find three numbers. Maximum possible is three. We find three numbers close to the keyword say cis or dia or anything. Since map, cis, and dia is in ascending order, like always map will be in the middle and cis will be the greatest number and dia will be the smallest number. Just by sorting, we segregate it.
So position is relative. It's not going to like always like cis come first and dia come second and map will be like third one. See, sometime map will be like in middle. Sometime it will be like top of the.
No, sir. I'm saying the numeric value, sir. Like say cis will be always say 100 or something. Dia will be always smaller than cis, and map will be greater than dia and smaller than cis. This is what
Okay. Okay. Good.
numerical sorting.
Okay. Good. So what in case like if one number is missing?
Sir,
Like suppose like your OCR is sometimes failing or maybe digit
yes, sir.
detection is failing. So in that case, how you are classifying this?
Yes, sir. In case keywords are not detected, first initially we search that slash keyword and we try to find the number before the slash assist and after as dia. And for map, we see for the closing and opening bracket. In case we couldn't find map, we are using the like the average value where like it is like cis plus 2 times dia by 3. That formula also we are using like cis by 2 times. Yeah, that formula we are using.
It's also good thing. Yes, you can let us.
Can you guys open the graph detection slide?
Yeah, just a second. This one?
Yeah. So can you explain that like so you're saying that like you're looking for a contour and then the largest perimeter will give that like graph and plotting the graph, right? So like this one like it is not like that similar, right? So why we are asking for like this is to like understand like the signals and like maybe like map it. So like how did you guys like decide to like come to this solution?
Sir, first of all, our main solution was to find out all the green color first.
by masking the image, and then we are finding out the largest perimeter. Like we are creating contours and finding out the largest perimeter. So that itself, and then we looked upon the net and we saw like upon which uh, perimeter should it be mapped, and so we got an idea like okay, one is to be there in seconds, the other should be in the amplitude of the signal. So that's how we mapped like.
Okay. 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 Thank you. Thank you. Thanks a lot.
Jitesh, Team 51 is in the waiting room.
Yeah. 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 So this is Team 51. Good afternoon, Team 51.
Yeah, good morning, everyone. Let me just share the screen and start the presentation.
Team 51, there is an announcement. There will be ringing a bell at 8 minutes and 9 minutes 30 seconds. So
Mm-hmm.
please listen to the bell.
Yeah, sure.
Okay.
Can we start the presentation now?
Yes.
Yes.
I hope my screen is visible.
Yeah.
Yep. So this is our submission for the Team 51's problem statement, which is vital extraction from medical monitor images. Um, a brief about this problem statement is that we have been given a monitor images with background as well, and we have to extract vitals such as SpO2 value from it. And now Shubh will explain about the data sets.
We were provided with three different datasets. The first of which had 2000 images of monitors along with the annotations of the monitors present in the images as shown in the first image. And the second dataset was classification dataset, which had 250 images each of four different types of monitors along with annotations of the given vitals and the graphs. And finally, a third dataset of 7,000 unlabeled images was provided to check for further exploration of the model on the basis of that dataset. And now Sukriti will explain the pipeline.
The pipeline is divided into three stages. In stage one, we applied the DETR model fine-tuned on the step one dataset that was provided for monitor detection. Once the monitor was detected, we cropped out the monitor from the original image. In stage two of the pipeline, we used the DETR model fine-tuned on classification dataset that was provided for vitals detection and classification. After detection of the vitals, we cropped out the vitals from the monitor. In stage three of the pipeline, we used Parsec for text detection from the cropped out vitals to get the values of the vitals. And now Ayush will go in a bit more detail.
Yep. So I'll start from the first stage of our pipeline, which was the DETR model. It's a transformer-based model for object detection published by Facebook Research. And we basically had to fine-tune the DETR model. It is already a pre-trained model, and then we fine-tuned it with a train and validation split of 80:20. And about the hyperparameters, I'm going to explain after I explain the pipeline in depth. And this is a state-of-the-art model. So first we do the monitor region extraction, as you can see a sample output on this side of the screen. Then on the second stage of the pipeline, we had to find the regions of interest, which is the vital bounding boxes. So we again trained a DETR model. We again fine-tuned a DETR model on six classes, which is HR, SPO2, RR, etc. And we gave it the same training to validation split of 80:20. We tried to improve upon at this stage by using semi-supervised learning. I'm going to talk about it in the improvement section of this presentation. Basically, there is an unbiased teacher model published by Facebook Research that could use unlabeled data to make the models better. On the third stage of the pipeline, we had to do syntax recognition. Uh, So basically, for this, we used Parsec model. It is a SOTA model which has 98.5% accuracy on the ICDR 2013 dataset, and it's sufficient for our purposes. Besides, we didn't have labeled data with us with the textual values of the vitals. So, so we couldn't fine tune this model any further. And besides, it's not worth it given that it already has a 98.4. But still, some of the images were hazy and stuff. So if we did have the data, we could have made it better for our problem statement itself. Now, I'll talk a bit about the hyperparameter tuning that we did. So I'll talk about the DETR model because that's what we fine tuned and not the Parsec model. So in the DETR model, we had a dropout regularization of 0.1. We kept this to just make sure it generalizes well because we had a lack of data. So we had to make sure that it's not very sensitive to outliers or something. We kept a batch size of 4. This is again in accordance with something which Ayan Goodfellow et al. Recommends.
So powers of 2 are usually good for GPU utilization, and smaller batch size is something that is very recommended. And learning rate is the default 1 - 4. It worked good for our purposes. If the models were not converging, then we would have maybe changed that. And we went for 20 epochs on the DETR model for both the fine-tuned models. And these are the graphs that we got for the loss and mean average precision. Now the evaluation metric.
Yeah.
Atul will,
Yeah, we used following evaluation metrics to evaluate the object detection model. Our first DETR model gave average precision of 0.954 in IOU range of 0.5 to 0.95. And our second data model gave average precision of 0.765 in IOU range of 0.5 to 0.95. Although, yeah, it is less than the average precision in first model, it is still good in object detection. Now, Sukrit, you can continue.
So, yeah, I'll talk about the challenges faced in this problem statement. So, firstly, we had a lack of label data. We did not have data which would tell what the textual values of the vitals were for a data. And we also had less accuracy on some of the pictures in the unlabeled data set because they had very lower resolution. Uh, so we'll talk about how we could have tackled both of these. For the first one, we actually tried to use semi-supervised techniques for boosting the accuracy. So basically, we had already a pre-trained model of DETR which we could use as a teacher model, and then we were trying to extract a student model with some boosted accuracy, but it really did not give us much better results when we compared with the loss and stuff. Uh, for the second point that we mentioned in the challenges, we could have used super resolution of the images using SR GANs, or just try to remove the noise and haziness from the pictures, or maybe use some kind of data augmentation to make it better. Uh, we did not really have we went through the SR GANs training. So yeah. As far as the good points of our models are concerned, it really does not depend on the monitor type that we use. So we did not really take any classification into consideration based on the monitor types, because although there were 4 classes with the same layouts, but the values within those layouts would have been rearranged in any fashion. So it didn't kind of make any sense to hard code those monitor types into our code. And so it's kind of not biased towards any particular monitor type. And the DETR model for the vital extraction also works because there's a standard color coding into certain vitals, such as I think, if I remember correctly, SpO2 is meant to be green or something. We actually looked into that. So on a few images from the unlabeled dataset, we did test our model, and it worked pretty well from what we could see. And
Uh,
now towards the graph digitization. Yes.
Yep. To digitize the graph, we first grayscaled the graph and sharpened the image using CV2 kernels. We used edge detection to get the edges of this sharpened graph, and then found the contours of these edges. And to avoid noise when plotting the contours, we put a threshold on the distance from point to point. To get the value of single Y for single X, we can do the average on them. Yeah, thank you.
About this graph digitization thing, we actually didn't put it in our code. It was just an attempt towards the graph digitization, and at the end of the problem statement, we didn't really have the type to to put this another notebook inside the main notebook of ours, and it was a bonus problem statement. So yeah. So
Okay, like we had actually asked for heart rate digitization, so that was a SpO2. So
yeah.
Okay, so I have like a few questions about like challenges that you have faced, right?
Mm-hmm.
Can you please go to this slide? So one thing is like you said lower resolution, right? So what do you mean by like lower resolution? We have provided all the images the same resolution. It's
Yeah.
yeah, it's 1280 by 720.
Yes. So 1280 by 780 is the resolution of the entire image, which also includes the background, which also includes the of which monitor is a small part. So now you have to crop out the monitor from this 1280 into 720.
Yeah.
And when you
Uh,
crop that out,
hmm.
then it's less.
So even if it is less, right? So I think like you will get more than like 70% of the area because monitor is not like I mean like very small. So in few images you might like face that problem, but it's not like data is not like low resolution.
Yeah, it's not exactly low resolution, but in the cases where it was low resolution, it wasn't able to detect that
Okay.
properly. So
Yeah. Okay. And I have like few question about like hyperparameter tuning. Uh,
yeah. Yes.
can you please check?
Hmm.
So you said like batch size was dependent on like GPU, right? So how do you like
Uh,
uh
yeah, so it is batch size. It's a recommended practice to actually use powers of two when you are using the batch size.
oh, okay.
Because
Hmm.
it is said that it powers of two help in an effective GPU utilization. So
Yeah.
if you don't have a
So,
power of two,
hmm.
it's not really
So is
utilizing
there
GPU.
any
So
specific reason you have choose 4 year?
uh, there's a not exactly a paper, but an answer by Ayan Goodfellow who suggests that lower batch sizes are preferred, and we had like 1600 images in the training data set, so it was divisible by 4, so we went for batch size of 4,
So
and
you
it's
have like
power of 2,
yeah,
and it's
okay.
less.
You have like trained this on GPU, right?
Yes, we have trained it on GPU.
Yeah. So what's the configuration of the GPU? How much memory does it have?
So the GPU is 1080 Ti,
Hmm.
NVIDIA 1080 Ti.
Hmm.
As for the memory, I'll have to check. Actually, it's on the HPC of my institute, and
Okay,
I have,
okay. So you are deciding batch size based on like the papers, right? What they say to recommend.
yeah, what the
Not,
leaders
not
in
yeah,
technique
okay.
recommend.
Not based on like what GPU you are using, right?
Yeah, not based on that.
Okay. Jitesh, you can ask.
So this one, like if you go to the monitored like detection and after you crop the image, like did you use any tilt transform techniques or anything to adjust the tilt?
We initially thought that we should, we could modify the DTR model to instead of giving some kind of a bounding box, it could give us 8 coordinates, and then we could use a perspective transform on that. But uh, we didn't really go with it because bounding box felt good enough for our purposes. And no, we did not create any tilts or something. We just passed we put an ensemble of all the monitor images, and then we just trained the second DTR model on it.
Okay. So and then like one challenges faced slightly. So there was a lack of labeled data, right? So
Yes.
like in the unlabeled like data, like so it was supposed to be like the classes, right? Like the labels. It was supposed to be a guideline. So where you guys can like then like do some more uh, like labeling and all of those like sorts. So when you face with this challenge, like so, what was the thought process behind like going on the said uh, uh, on the like how you chose to like solve this problem?
Okay, so an obvious approach would have been to label the unlabeled data, but we did not really want to go for it because that kind of felt like cheating. I mean, if you have a labeled data, you could always get more labeled data by collecting more datas, and that's good enough. But we wanted to have a model which would also utilize the unlabeled data instead of, us having to manually sit and generate label data. So to do that, we came up with an approach of semi-supervised learning. So we have like few labeled datas, and then we have a bunch of unlabeled data, a lot of unlabeled data, and then we train a model on that labeled data, and we call it the teacher model, and then we pass it through a setting, semi-supervised setting, where we put this teacher model into it, and it gives us a student model. And this student model is also is trained on the unlabeled data set too. We basically pass the unlabeled data set to the teacher model and then do some computations on it to find out how similar they are. And that's basically the idea of semi-supervised learning. So most of the state-of-the-art models in that. So for example, I think unbiased teacher by Facebook Research is an is a model in that direction, and it offers like on if you take 10% label data of the COCO data set, it's giving I think around 30% accuracy on the entire after getting trained on the rest 90% unlabeled data set. So it works, but in our case, it did not really prop up the accuracy so much. I mean, there we could go in, we could explore more of the other models for semi-supervised learning, like unbiased teacher was, I think, still pretty down on the list of SOTA models. We could have tried other SOTA models. Some of them are actually not open source. So yeah, we'll have to look into that.
Okay, I
Okay.
have one question. So you said like you are using a teacher model and a student model, right? So what was the
Mhm.
purpose for behind using student model?
Uh, so the student model learns from the teacher model. Teacher model is
Yeah,
actually
so
pre-trained.
teacher model is already giving you like correct levels. That's the purpose of like teaching, right?
N-
So why
No,
can't
the
you
teacher
direct?
model.
Okay.
Yeah, good.
So why
Yeah.
can't you like directly use teacher model? What's the purpose actually serving the student model over there?
Yeah, so teacher model gives us correct accuracy for most of the for a lot of the images, but
Okay, okay.
the
Then
point
how
is,
the student model is learning that where teacher's model is failing?
yeah, so different architectures approach these problems differently, and so so the teacher model is basically like some you train it on a small part of the entire distribution, and it gives you a good accuracy on that particular small part, and then you want to somehow use the unlabeled data set to to prop up the accuracy of that. And so this teacher model, you pass it an image, and they are, I think, in unbiased teacher, they are connected in some kind of an adversarial setting. So you pass some data set to the teacher model, it does the prediction, and then you pass the some unlabeled data set from this student model, and then it again does the prediction. Then they are combined with some sort of loss function, and uh, they
Okay,
try to
okay,
help
got it,
prop
got
up the accuracy.
it. Thank you, guys.
Okay. So the presentation's over.
Yeah, yeah, yeah. Thank you. Thanks a lot.
Yeah,
We can close this.
yeah. Thank you.
So this is team 23.
Yes. Wait, actually, I guess others should be joining.
Okay, cool.
Name is not okay.
Ish, can you
Okay.
touch it as is
Okay. Yes, yes,
following
yes.
naming nomenclature?
Should we remove them?
Wait, actually. Ask Halted to change it.
Meanwhile, I request
Yes,
Team
actually.
23 to listen to the bell. We will be ringing at 8 minutes and 9 minutes 30 seconds. The
Okay.
bell is.
So Akash, what do you want us to do? Like,
Harshit is not following the name nomenclature like Team 23 dash Harshit.
Yes, yes. We are asking him to do that. If he has not problem, he will leave.
Okay. Can you please do it faster?
Yes, yes, we are telling him.
No. Uh, just to confirm, Team 23, have you listened to the bell?
Yes, we could listen.
Okay.
Okay. Um,
okay, please start.
Weber, start the screening. Hello, Weber.
Bro, one
Please
second. I'm
start the
like presenting
presentation.
the slide. I'm
Yes.
presenting the slide, man.
Okay. Okay. Do it quickly. Okay.
So is the size visible?
Yes.
Yes,
Okay.
yes.
Okay. So good afternoon, everyone. Thank you for joining me today as I present our project on developing an model for extracting vital signs from ECG monitor images. So in our quest to provide a more accurate and efficient system for monitoring patient vital signs, we have tried many approaches, but none have been as effective as the transfer learning based multi-layered pipeline we have developed. With this approach, we were able to easily locate errors in the model as it has an interpretable pipeline, making it easier to make adjustments as needed. So this is our pipeline architecture. So a model expects an image of an ECG monitor as input, and it outputs a Python dictionary with all the vital labels and their values, including the matplotlib plot of the heart rate digitization graph. Our model generally mimics like how humans interpret and monitor view. So not only is the model very accurate, but also it is scalable. So we can add many sub pipelines to it to make it perform even more complex tasks. So I'll be discussing the development process of the model and its features and the capabilities and how it can improve the patient monitoring. So let's dive in. So for the monitor segmentation part, we have developed a monitor segmenter that uses YOLO v5, which is the current state-of-the-art model for the quick object detection. The model is trained to detect ECG monitors in images and output the X center, Y center, height, width of the monitor. By using this information, we can crop out the monitor. So we can crop out the monitor and focus our attention on the vital signs displayed on the monitor. So during our testing, the monitor segmenter was able to the monitor segmenter was able to accurately detect the monitor in the images with high degree of confidence. So the average precision score for the model was above 95%, which indicates that it was able to correctly identify the monitor in majority of the images. The monitor segmenter is a crucial component for a pipeline as it makes the monitor segmenter is a crucial component for a pipeline as it makes possible to extract the relevant information for the images plus also use them to the monitor of the patient vitals. By using this model, we can automate the process of tracking vitals and making it more efficient and accurate. From here on, my teammate would take it.
Once we have obtained the cropped out image of the monitor, we try to classify the monitor to the closest class it represents in the unlabeled dataset. For doing so, we have used Inception v3, which is a for that we have used an Inception v3, which is a model trained by Google, which was trained on ImageNet dataset. It is an unsupervised learning architecture where where we extract the feature of the which extract the feature of the images, and those images we then use k-means clustering to classify into the 4 nearest classes. So by doing so, the biggest advantage was we were able to obtain 100% accuracy over our dataset, training dataset. With this, we will proceed to the next stage. Vaibhav, next slide, please. Once we have obtained the class of those things, we pass the cropped out image to a digit segmental stage. If here we have a machine agnostic YOLO v5 model which only crops out the digit from each label dataset. The model returns the x center, y center, height, and width of the segmented digits, and we only take the top 6 values based on their confidence scores so as to prevent any form of false positives. We trained the model for 30 epochs with a best size of 30, and the results were encouraging, which we would encapsulate in our next slide. This table quite clearly tells us that the precision and the accuracy, as well as the bounding box error, which was minimized by the YOLO v5 model, has performed very well. Hence, this classification is able to detect the digits over our dataset very well. Please move on to the next slide. Once we have obtained the segmented digits and the 6 label dataset, what we try to do is we try to classify the 6 digits. So using the four parameters that were x center, y center, height, and width, we try to classify them in the 6 label classes, which is similar to the process in which a human would evaluate an image. For doing this, we did not use any deep learning approach because the data provided to us was very limited. Instead, we used an XGBoost, which is an powerful ensemble model, which gave a very good performance over our training data set. As it has been encapsulated on the side table, we were able to obtain upwards of 97% accuracy over our classes, all 4 classes. By doing this, we have obtained the 6 labels as well. Now it is part of the final stage for vital recognition, which is the OCR part. For OCR part, we tried many different OCRs, whether it was PyTesseract or Calamari OCR. But at the end, we settled with Easy OCR because it had a feature where we could actually filter out the data and only allowed the numerical values to be labeled. Also, before completing this OCR part, what we did was we tried to increase the sharpness of the image, as the image provided were at times blurred and there was noise in them. Also, OpenCV's auto brightness feature were used so as to reduce the glare of the images. By doing so, we obtained a satisfactory performance. And the next part would be our heart rate digitization. Heart rate digitization in our model is a separate pipeline, where instead of which is separate from the vital extraction part. Here, what we do is, given any image, what we have is a YOLO v5 model again, which only classifies the heart rate from each monitor. Then the heart rate which we have taken, we pass it into an OpenCV function which we have created, which does a contour detection over the images. First, we straighten the images so that all the Y values align. And then we use our contour detection to obtain boundaries. We preferred contour detection over eye detection, as here we would get
Hello, Archit.
I think there might be network issue.
Yeah. We lost at the part of when they're trying to compare between edge and contour. The
So yeah, we're open for questions now.
So like we actually lost Archit, like his video
Yeah, we
froze.
lost actually in the middle. Mm.
Can you go over that part which he was
Yeah,
talking
one
about?
second. Uh, so basically for heart rate digitization, we have made a separate pipeline. We have trained a YOLO model to get the heart rate out of it, and then we have applied the counter detection OpenCV feature. And then like that, we have applied the heart rate images for detecting the points, and then we prefer the counter detection over the edge detection as it was giving more continuous slow responses instead of the discrete labels. And then also before the images were straightened to align the peaks at the same level at same places, we obtained multiple y coordinates on single x. To resolve it, to we have took the mean at such places and plotted it using the matplotlib library. So this is the end of our presentation, and if you have any questions, we are open for questions.
So like you said like you choose 6 digits based on a confidence, right?
Six
Like
days based
using
on.
so like
Mm.
so the top six like digits using in the monitor segmenter
Yeah, top
part.
6 digits. Mhm.
Yeah. So how did you like come like so those like 6 digits, right? So there are like so many like many other like digits. What was this confidence score like based on?
So the confidence score was based on like by using YOLO, we got all the digits which were segmented. So we
Hmm.
got all the segmented digits, and from that we have applied OCR to get the number out of it. And thus for
Actually,
labeling all the vital labels, we have used XGBoost, which is a random supervised learning model for
yes.
labeling each OCR.
For the 6 digit part, I would like to say there were some cases where it was also predicting some random values. It was even detecting background as a digits. So to sort it out, what we did was we added a heuristic function where after passing it to the OCR, we were seeing that digit which it was passing. If it was giving some random values, for example, if it was giving me an empty string, then we were not considering such data. We knew that it was wrong. So there was a heuristic as well as our 6 confidence score to sort this problem out.
Okay. So you use easy OCR, right?
Yes.
So like you didn't you like face any problems with respect to the forward slash in the BP? Was that considered as like
Huh, yes, yes. So actually, I think that was a big problem which we solved by using easy OCR, because unlike PyTestRect, it allows us to actually filter out the data. So we had a pass range, a filter range, which would be 1 to 0 all the digit, as well as the bracket and slashes. If easy OCR was detecting any slashes, then we were splitting the data at that point of time using Python, and we were reporting the first digit as SVP and the other as DVP. So that was our filtering from our end, and also easy OCR was again one of the reasons we use it. We use it.
okay. Pradeep?
Okay. So my question is like, so when you do OCR, right, you need to have like digit as a straight image. If like sometime monitor is tilted or something, right? So you will get a digit that is also like tilted. So in that case, that slash is not interpreted as a slash but as a one. So are
Yes.
you doing like any pre-processing step before passing this digit detector?
We actually tried binarizing the digits, but actually the noise was very bad on the output in the input. So the results which were obtained by binarizing it were worse than when we were passing directly the color images. Also, what we did was actually, as you have told us, that sometimes it was also reading the slash as 1 and sometimes as well as 7. So to sort this issue, we added a padding on the cropping boundary. So instead of taking the direct boxes, we were taking some extra part as well. By doing so, we were able to get it. But again, there was some cases it was interpreting it as 1. But suppose if the value was 121/35 as an assumption, so it would be reading as 121,135, which would be a 6 digit number, which SVP, it is not possible for SVP to be in that range. Again, there was a heuristic, which if the length was greater than 5, we were taking only the first 3 digits for SVP and the last 2 digits for DVP.
Okay. Yeah. Thank you guys. Thank you.
Okay.
Okay.
Thank you for your time.
Thank you. Thank you all.
Thank you.
Good afternoon. This is Team 11. Good afternoon, Team 11.
Good afternoon, sir.
Good
Good
afternoon.
afternoon. So, just give us a second. We'll like start in a minute.
Team 11, there's an announcement like before, like after 8 minutes and 9 minutes 30 seconds, we'll be ringing a bell for like. So I'm just ringing the bell so you can listen to it. Is it okay? Okay, let me
I
do it
couldn't
very
hear.
quickly. Is it still not audible?
No.
Just wait a minute.
Are you able to hear us?
Yes, yes.
Okay, I think Akash. So what Akash was saying was like that there will be a warning bell at 8 and 10 minutes. Akash, so like, can we go ahead?
Yes, we can start.
Yeah. Okay, cool. Guys, like, please start the presentation.
Good afternoon, panelists. We are Team 11, and this is our presentation for Cloudphysician's Vital Extraction Challenge. Our problem statement requires us to extract vital health information like heart rate, SpO2, respiratory rate, BP, and MAP given the images of a health monitor. Continuous patient monitoring is required to ensure speedy response in urgent situations. Hence, automating extraction of vitals with high accuracy is absolutely necessary to scale this procedure across numerous ICUs. Now let's look at the pipeline. Here we present a robust pipeline which includes segmentation and object detection, followed by optical character recognition or OCR. Moreover, in a few cases where object detection fails, we employ a novel technique for vital extraction using image processing and clustering techniques followed by OCR. Let's quickly get an overview of the data. A segmentation dataset of 2000 images with ground truth marks for screens, a classification dataset of 1000 images from 4 different monitor classes with bounding boxes of all the vitals, and an unlabeled dataset of 7000 images were given. Pradipta, you are on mute.
Sorry about that. The first step to our pipeline is segmentation. This is a classic semantic segmentation problem with two classes, screen and background. Followed by this step, we warp the screen to generate its top view in order to bring uniformity in screen and text orientation. We experimented on 3 models for this task, namely UNet, PSPNet, and FPNet, with ResNet 34 and EfficientNet V1 backbones for each. We will specifically focus on FPNet, which yielded best results for our case with EfficientNet V1 backbone. A feature pyramid network processes the encoder features at 4 different resolutions separately and concatenates them to get the final prediction mask. This enables the model to have better information about the global context. We show only 2 resolutions here for illustration purposes. Let us now look at the model performance in each of its ResNet and EfficientNet backbones given by IOU score against this inference speed 1 by 1. The 2 variations of UNet give decent results, about 86 and 79%, with an inference speed of 0.3 and 0.4 seconds per image. Followed by UNet, we next have FPNet, where the EfficientNet version gives about 96% accuracy with a speed of 0.25 seconds per image. PSPNet is not far behind, where the best model has an accuracy of about 90% and can perform inference in under 1/5 of a second. We trade off the inference time for a 6% boost in accuracy and finally use FPNet in the pipeline.
After we have segmented the monitor screen from the image, we perform the task of object detection to extract the bounding box of the vitals as shown. In our experimentation, we tried out various object detection methods, including both supervised and semi-supervised detection methods. So beginning with fast RCNN, it is an object detection model that generates candid region proposals with the help of a region proposal network. The region proposal network is trained to predict the objectness scores for each proposal, along with its bounding box coordinates. Next, we have the YOLO V7 model. YOLO, in principle, divides the input image into S cross S grids and finds the probability of an object lying each and every grid cell. Each grid cell is responsible for predicting the bounding box and scores for those boxes. For our data set, the YOLO model was relatively faster and more accurate than the fast RCNN for the classification data set. Next, we tried the single shot detection method. The SSD architecture comprises of a VTG16 base network with a multi-box convolution layers at the end. The convolution layers progressively decrease in size that enable to detect objects at multiple scales. The inference time that we got for this model was 3.14 seconds with an MAP of 99.3. We observed a significant increase in MAP using SSD compared to the previous models with little trade-off in inference time. So on top of the SSD, we tried an interpolation-based SSD, which is a semi-supervised learning method. So it works on top of the SSD learning from that we obtained earlier. So the way this works is that we interpolate samples, and I'll explain that. So we take two images from the data set, and the HRW class and the HR class from two images are interpolated together with a weighting factor to give the interpolated sample. The model is trained to give predictions on these samples to be consistent with the individual images. With the ISD model, we got an MAP score of 99.4 in the validation set with promising generalization on the unlabeled data set. When the foreground classes are interpolated together, the JS divergence loss is used. And when foreground class is interpolated with a background class, a KL divergence is used. So these cases are handled separately. Together, they form the ISD loss used in our training.
Next, we use OCR for extracting the values of the vitals from the OD bounding boxes. We tested SOTA OCR models, keeping in mind the importance of both accuracy of text recognition as well as inference time. We have manually annotated the bounding boxes of 200 classification images for reporting our results in the following slides. PyTesseract OCR engine is a LSTM-based OCR engine that performs connected component analysis and contour thresholding. We have applied pre-processing techniques on top of that, like padding, Otsu thresholding, and skew correction before OCR. Parallel OCR framework is a scene text recognition model that returns all detected text within an image. Keras OCR uses convolutional recurrent neural network for text recognition. The segmented image is cropped using the bounding boxes from object detection and sent to this OCR model. TR-OCR is a transformer-based vision language model. Of all the models, TR-OCR provides the best accuracy of 95.76%, but its long inference time of over 50 seconds makes it a poor choice in a practical pipeline. Here, we have provided a comparative analysis of accuracy versus inference time for all our candidate OCR models. As we can see from the plot, the fine-tuned Keras OCR model with Onyx is the optimal OCR model with the best accuracy time trade-off. We can see here as a orange dot. Let's look into how we have fine-tuned the Keras OCR model. We use the ground truth bounding boxes from the classification dataset. We inferred these cropped images through the TR-OCR model to generate ground truth labels. Then, all the layers of Keras OCR model were fine-tuned, and Onyx was used for quantizing the model, resulting in a significant decrease in inference time.
In a few cases, our object detection model detects bounding boxes correctly. However, it labels them wrongly. For a particular label, when bounding box has low confidence, for example, less than 80%, we try to find the label using the image processing plus clustering framework. As you can see here, HR is misclassified as SPO2. We have tried to solve this problem with the unsupervised clustering technique. Now we are taking a case where the bounding boxes are detected, but the label confidence code is low. First, we have found out the contours using OpenCV library, as you can see in the output. Next, the experiment we have chosen on the unlabeled dataset of 7,000 images. As you have observed, there are more than 4 types of monitors. Then we use DenseNet 120 architecture for extracting features and then applied PCA, where we use GMM clustering for as it's a very good algorithm for contextual information, and use AIC method for getting the number of clusters, which is 15 for our case. Here is a cluster-wise 2D feature projection, and you can observe how different images with similar patterns come inside of the same clusters. Here we're going to understand how clustering helps us, but the object detection model is not giving the proper output. For this case, we're going to use the cluster, going to find the cluster ID using GMM central distances. The bounding boxes can be found or extracted from the predefined set of bounding boxes, and we are use TR-OCR for getting the values from the contours. Hence, we are going to match it with the HR level or the failed image.
Efficiency of our pipeline for different types of OD and OCR models. Here we can see that ISD 512 with Keras OCR model gives 85% with 6.5 seconds of inference time. But we have made it even better by fine-tuning it through TR-OCR and quantizing the model. And our final pipeline time comes down to about 5 seconds. And we have used FPNet for segmentation and ISD 512 for object detection. Finally, we shall address the problem of digitizing the HR graph. After object detection, when we get the bounding boxes of HR graph, we crop the image and we apply image processing like connected components area threshold. And from the binary image, we detect the height of the white pixels and get the matplotlib plot. Here we see the animation of the HR digitization process. Thank you everyone for listening. That's all from our side. We are open to questions now.
Thank you. A very good presentation. You guys have done good analysis of each stage as well. So very good. Pradeep, you start. I'll come up with the next question.
Yeah. So can you show me that interpolation slide? Just I have one question about it.
Yes, sure.
Okay. Here you are taking samples, right, and trying to interpolate it. So my question is this one in this example there is one number and one is a graph. So you are interpolating both and associating that HR with HR wave, right? So HR means a number. So what will happen if there is a graph is missing, or maybe graph is there and number is missing?
Yeah.
So this is not exactly a graph and a number method. This is actually applied for any of the classes, including all of the classes. So it can be HR label and the SPO2 label also. So with the interpolation method, we are actually making use of the large amount of unlabeled data that we have. And so this is, we're not using the ground truth in this step at all. So purely based on the earlier model predictions, when the model is predicting the objectness score, that is that there is an object in both the images at this point. So we interpolate them. So with this, actually this helped the model to tackle the cases where many labels are appearing close to each other. So in that case, we got better results.
Okay.
Yes, Jitesh, you can ask.
You guys finally decided on which OCR, which
Yes.
one?
So we have finally used Keras OCR, but we have fine-tuned it for our use case as well as used Onyx for reducing the inference time.
Okay.
Yeah.
Fine tuning, how did you fine tune this one? On
Yes.
top of that?
So Pradipta, can you move to the fine-tuning slide?
Yeah, sure.
Yeah, so for the classification dataset, we already had the ground truth bounding boxes. So what we did was we cropped those images for just the numbers and not the graphs, and we passed it through the TR-OCR model. So TR-OCR is a very accurate model which almost always gives the number perfectly. However, we could not use it for inferencing because of the inference time. So what we did was we used TR-OCR for getting the ground truth label. for training the keros OCR model.
I think like there is a noise disturbance. Like
Yeah.
one of I think Pradeep too. Like, can you mute Team 11 Pradeep too? Can you mute? Or wait, like yeah, okay. Yeah, please go on.
Yeah, so we have fine-tuned the keros OCR model using the labels from TR-OCR. Like
Okay,
we have generated the labels. Yeah.
okay.
So it actually increased our accuracy by 10% than the pre-trained keros OCR on the synth 90K dataset.
Okay, cool. Okay, yeah, cool. It's a good presentation. So, but like we can close it. Close it. Thank you. Thank you all.
Thank you.
Thank you.
Thank you.
Thank you. Yeah. Hey, Abhinav. Okay. So like you want to let the this one meet go on, or like shall I just end it? So do you want like so we have the recording on, right? So can we like close the this one meet? I can send you another meet link. Yes. So this will be like session 1, right? So yeah. 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 Okay. Cool. Let me stop the recording. Okay, cool. So we'll meet in some time.
Okay.
Yeah, thank you. Yeah.
Okay.
So 2 o'clock, right?
At 2
2
o'clock.
o'clock. Okay, cool. Thank you.